Hi everyone. Sorry to be missing out on you today. We do have one quick lesson to cover today, and actually our lesson, it's more like half a lesson. Just to give you some background on where this lesson is coming from. Your textbook in chapter 11, we work pretty much straight through the chapter, but section 11.3 is the section on factoring, and they kind of hit all of that factoring that we did all last week in like one tiny quick section. It's like, hey, by the way, here's what it means to factor something, and then they kind of expect you to figure out all of the different types of factoring on your own. I'm not a fan of that, and so that's why last week we spent all of that time doing all the different types of factoring. Now we're kind of coming back and wrapping up loose ends, so this is all from section 11.3, which is where all of the factoring would have been located. Today we're just kind of covering the rest of the stuff in 11.3 besides all the factoring that you did last week. So this is more like I said, like half a lesson that we're going to cover today. The other thing that kind of stinks about today's lesson is there's a couple of like connections and just some information that we're going to cover here that leads to some connections we're going to make in some future lessons. For today, it's going to seem kind of like magic. It's going to seem like, hey, by the way, if you do this one thing, this happens, okay? When we haven't actually learned the why yet. That's coming in section 11.5, which is 2 days from now. So there are a couple of things that you kind of just have to take a leap of faith with me today on. And when we get to that section 11.5, I'll circle back and show you the why behind the stuff that we're talking about today. So you should have these notes in front of you, factoring special cases, lesson 11.3. And again, technically 11.3 covers this little bit of stuff plus all the factoring that we've already covered. Okay, so I'm going to go ahead and turn my face off because you don't need that. And let's take a look then at some vocab here. So when we're talking factoring, all right, the word prime refers to something that cannot be factored. And we sort of mentioned that last week, but anytime I'm saying you cannot factor it, we can call it prime. Something that cannot be factored. And if you think about prime numbers, those are numbers that cannot be factored as well. So like the number 7, you can't factor 7 other than 1 times 7, okay? So it really means the same thing with polynomials as it does with just numbers. And then I just want to remind you about rational numbers and real numbers, okay? And really what's important here is the difference between the two. Technically, the definition of rational numbers is the set of any number that can be written as a fraction. So that's the mathematical definition of a rational number. Okay. Now I do want to point out when we're talking polynomials, okay, which is what this whole chapter is about, if I say to factor it over the set of rational numbers, that has a very specific definition that actually is talked about down here in example 1. But see where I say set of first-degree polynomials with integer coefficients? Okay, that's what it means to factor over the rational numbers. So if I'm saying to factor, that means you want to use whole number, technically integer because they can be negative, but whole number coefficients. And if you're calling me out and saying, wait a second, you just told me that fractions were okay, you're absolutely right, okay? I'm messing with you a little bit here, but when I say to factor and I say to use whole number coefficients, the reason for that is we're eventually going to learn that a factor that looks like this actually has the same significance as a factor that looks like this. Okay? You don't see the connection between these two yet, and that's okay. But there is a connection between these two, and that's one of the things that's going to come up later this week. And so instead of writing our factors with fractions like this, we would want to write with whole number coefficients. Okay? So now, when we talk real numbers, what do we throw in besides the rational numbers? Well, the real numbers are all of the rationals, but then also all of the irrational numbers. And when I open the door for irrational numbers, that allows you to use a lot more, that gives you a lot more possibilities. Now, irrational numbers, what everybody always thinks of is pi, okay? And that's true. Pi is an irrational number. It's a fraction that goes on and on forever. But for our purposes today, the ones that are going to be the most important are the square roots of numbers that are not perfect squares, okay? So think about taking like the square root of 8 in your calculator. You're going to get this big crazy decimal. That is an irrational number. And so if I say to factor over the set of rational numbers, which by the way, all of the factoring we've done so far has been living in this land, rational numbers. And 95% of the factoring you do in your entire life is going to lie in this land, okay? Almost always when I say to factor, we're just talking rational numbers. But if I specify you can use any real number, now these things are on the table when they weren't before, okay? All of this will make sense once we do a couple of our examples, but I just kind of wanted to throw those out there for you. Okay, here's our other thing that is sort of, seems like it's very far from out of left field, talking about the discriminant. Like, what the heck? This is from chapter 6, right? But the discriminant theorem says that if you find the discriminant of a quadratic trinomial, which all of the trinomials we've been working with so far have been quadratics. Anything that's got that x squared and the x and whatever, those are all quadratics. If you have a quadratic trinomial and you find the discriminant, and the discriminant comes out to be a perfect square, then we know that the trinomial can be factored. So I want you to think about the implications of this. Because when we first talked about like not being able to factor something, the question came up, well, how do we know? And my answer was always just, well, try to factor it. And if you can't, then it must be prime. And a lot of you don't like that. A lot of you want to know, can it be factored or can it not be factored? That's what this does, is this is a test to see whether or not something is factorable. So let me give you an example. If I give you the trinomial x squared plus 5x plus 4, and let's say you are just spinning your wheels on this one and you cannot figure out a way to factor this one, okay? Hopefully you're not spinning your wheels on this one, but I wanted to start with an easy one. What you can do is you can find the discriminant, and the discriminant, if you don't remember from chapter 6, is b squared minus 4ac, ignore that dot, that makes it look like division, which means we would do 5 squared minus 4 times, my a value is a 1 times 4. 25 minus 16 is 9. Okay, 9 is a perfect square, so yes, this can be factored. Yes, it is factorable. Okay? Now, that 9 doesn't actually help me with the factoring, but it does confirm for me that I am able to factor this. And again, the reason for that is that this is a perfect square. Okay? And so we could then say, okay, I'm going to try a little harder and try a little harder, and I'm going to think about what multiplies to 4 and adds to 5, and then I'm going to have this epiphany, and I'm going to realize it's x plus 4 and x plus 1. Okay? Because 4 times 1 is 4, 4 plus 1 is 5. So that's just the factoring we were doing last week. But again, the fact that this 9 came out to be a perfect square confirms that this is possible. That's all it tells you, is that it's possible. The 9 does not have anything to do with the actual factors, okay? But then let's say I gave you one that looked really similar to that. Let's say I gave you x squared plus 4x plus 5. And you were spinning your wheels and you couldn't figure out how to factor that because you couldn't think of a way to multiply to 5 and add to 4 with them both being positive. So you tried the discriminant on this one. And you did 4 squared minus 4 times 1 times 5. Let's see, that's going to be 16 minus 20, which is negative 4. Okay, and I picked a bad example here because, well, 4 is a perfect square, right? But the fact that it's negative means I would have to be using complex numbers to do a square root, and that means it's not as pretty as just a perfect square like 9, okay? So this, because this is not technically a perfect square besides using complex numbers, okay, not a perfect square, this was not factorable, okay, which means we would call it prime. Okay, so technically this is possible if we're allowed to use complex numbers, but we're not right now, okay? eventually we are going to get to the point where we're using complex numbers. But so technically, could you go through and run the discriminant on every single factoring problem I ever give you first? Sure, you could. Okay, I think that's kind of a waste of time if you ask me. But if you were on one that you were really stuck on and you couldn't figure out the answer and you're feeling like maybe this is a prime one because I can't quite find the answer, this is a way to test, okay, is by finding the discriminant, deciding if it's a perfect square, and if it is a perfect square, you should be able to factor it. The reason why these two things are connected is coming up in a later lesson, okay? For right now, I realize this probably feels like it's out of left field, but the reason why is coming, I promise. Okay, so let's take a look at this one. Example 1, can this polynomial be factored over the set of rational numbers? And again, first degree polynomials with integer coefficients, that's really just what we were talking about up above when we said, can I use polynomials like this? Okay, this is factoring with rational numbers. Everything you've been doing so far, again, is rational numbers. Okay, so to answer the question, can it be factored, I can check with my friend the discriminant. So in this case, it would be negative 2 squared minus 4 times 3 times negative 5. Let's see, this together is going to be 60, and this is a positive 4, so this is 64. This is a perfect square. So my answer is yes. It absolutely can be factored. Okay? Once I know that it can be factored, I'm going to go ahead and factor it. And that's, again, using the same rules that we did last week. This is one where I would multiply these two things together first. So I know I'm looking for a negative 15. And here are my ways to multiply to 15. And I want a combination that's going to add to negative 2. And I do need one of them to be negative because it's a negative 15. So I'm looking at this one right here because I know I can make a 2 out of that. And I would want my 5 to be negative because 3 and negative 5 make negative 2. So then I'm going to plug these two things in for that negative 2y. This is all stuff we did last week. That's why I'm going so fast. Okay? You've done this before. 3y squared plus 3y minus 5y minus 5. So I just rewrote this polynomial. I used 3y and negative 5y to make my negative 2y. Pull a GCF from this and pull a GCF from this. So I'm going to pull a 3y, and I get a y plus 1. And over here I'm going to pull a negative 5, and I get a y plus 1. And that leads to factors of y plus 1 and 3y minus 5. So again, this number 64 did not actually help me find my factors. Okay? We are going to talk later in the week about a way that it's going to lead you to help find the factors. But for right now, there is no connection between the 64 and the factors themselves. But what you can tell from this is the fact that it's a perfect square tells you that it's possible, that it can be done. It's not prime. Okay? Excuse me. If I had more time, I would go back and edit that out, but I don't. So, okay. Example 2. Is x squared minus 6 prime over the set of rational numbers? And remember, this discriminant test that we've been doing, that's a test for the rational numbers. So, again, if I'm asking, is it prime or can it be factored, I'm going to check my discriminant. In this case, my b value would be a 0. Okay, so I'm going to say 0 squared minus 4 times 1 times a negative 6. And I come out with a positive 24. Okay, positive 24 is not a perfect square, okay, which means this cannot be factored, at least not over the rational numbers. Okay, so my discriminant test only applies if I want to live in the land of rational numbers, which again, majority of the time, you want to live in the land of rational numbers. And in fact, if I don't give you any specific directions about whether or not you're using rational numbers, you do want to still assume that you're in the rational numbers. Okay, Now, be careful about the wording of this question. So we said it cannot be factored, but the question says, is it prime? So the answer would be yes, it is prime. Okay, because prime means it cannot be factored. Okay? Now, for this next question, is x squared minus 6 prime over the set of real numbers? Now, all bets are off. I don't need it to be a rational number anymore. I can use anything that's real, meaning now I'm allowed to use square roots. Now I'm allowed to use crazy like pi and stuff. Pi is never going to really come up in factoring, I promise. But I can use almost anything I want, okay? Can't use imaginary numbers yet, but we will eventually get to the point where we are. So think to yourself, what kind of factoring problem does this look like? Okay, and I hope that you're saying, well, that looks like difference of two squares. Okay, difference of two squares, which those are usually the problems that look like, oh, I didn't mean to put a parenthesis there. Normally that's these kind of problems, right? But the issue is 6 is not a perfect square. So technically, I can't call this a difference of two squares. So think about x squared minus 25. We would factor this by going x and x. That comes from doing the square root of x squared. And then 25 is 5 and 5. 1 plus, 1 minus. And again, technically what I did there was take a square root of x squared and a square root of 25. And that's where these things came from. Okay? If I'm allowed to use anything that's real now, I can use this same method. Okay? I can do x and x, but just when I go to do this number, I have to use the square root of 6, which is a real number. It's not a rational number, but it's a real number. And I'm just going to leave it like that. I'm going to leave it as plus square root of 6 and minus square root of 6. Okay? And then that's it. That's factored. Okay? So the question, is it prime? No, it's not prime because I just factored it. Okay? And I know this is weird in factoring land. And again, normally we don't factor like this. But as soon as it said using the set of real numbers now means I'm allowed to use crazy stuff like this. Okay? So my question there, is it prime? No, because I was able to factor it. Okay, it's just a little bit different than something like this where this came out to be a nice happy whole number. Okay, so again, what we just talked about is sort of the extra stuff in 11.3 besides all the factoring. Okay, so technically all the factoring we did last week was part of this lesson too. Your homework for tonight is Lesson Masters 11.1 to 11.3a. So 11.1, 11.2, and 11.3a. All of that is in your homework packet, okay? And you have remaining class time to work through those. So 11.1 to 11.3a, go ahead and get started. And we'll make sure to discuss this some more tomorrow. Thanks for your time.